So we're now looking at the RL circuit. So now we're going to look at the RL circuit. So what you're going to find here is that, I'm going to sort of like mimic what we did before here. And what we found here is that you're going to find here that RL circuits behave identical, behave exactly the same as RC circuits. Now, I agree that there's two different processes that are going on. Okay, there are two different processes that are going on. And so our goal here is that we're going to take any RL circuit and convert it into a Norton circuit. So regardless how complicated the RL circuit is, we're always going to be dealing with the Norton circuit. So that means here that the Norton circuit has to do what? It has a current source, which is I short circuit. I'll have a resistor in parallel. And remember, the Norton resistance is the same as the Thevenin resistance, and then I'm going to have my inductor like this. So regardless of what this circuit looks like, we're going to always get it into that form right there. So I'm going to pick the exact same circuit that we did last time with the capacitor. And that is that we started with the voltage source, and we had 3 resistors. But now I'm going to replace the capacitor with an inductor, and then I'm going to have a switch that looks like this here. So you can see I could write this 1, 2, 3, and here's L. And our whole goal here is to calculate what is the current of the inductor as a function of time. This is what we're after right here. What is that inductor? And we're going to assume that we close the switch at t equal to 0 here. Now, this is not a course in Physics 4B. But a very, very common thing that's shown in fact, I've never seen this done actually in a circuits book, is that they'll use voltage divider rule, KVL, to actually solve this problem. Right? So, for example, if I was to go and calculate this guy here, we're going to open this guy up and put a short here. That short will kill this 3 ohm resistor, and then people sort of like do a KVL loop around this thing. That's actually not correct. And I'll see if I can explain it a little bit, but we want to be careful how we handle this. But I'm probably going to do the very wrong thing and just say, we're going to do it anyways, even though it is incorrect. And I'll make sure that you'll see what I mean by that. But I'll only do it once, and then I won't do it again after that. So what we're interested in determining IL of t for, we want to know what that value is at 0 minus. Right? Just like we did. VC is exactly like that. Then we want to know at 0 to effectively 5 tau. So that means for this, we're looking at this time right here. That's what we're most interested in. We're most interested in the transient period. That means it has gone almost to its final steady state value. It's not there, but it's 99.3% there. And then finally, we want to know what IL is at t equal to infinity. And according to this here, when this goes to a short, it kills that resistor. We can see that the final steady state value of the inductor must be I short circuit at t equal to infinity. That's what we're interested in. So what we'll do here is that we'll sort of like try to talk our way through this thing here a little bit. But, you know, before we get to the chase here, so what we're going to see here is that the solution to this circuit is IL of t. So there's a mathematical solution that we want to go after. It's going to be I short circuit plus IL of 0 minus I short circuit e to the minus t over tau. Okay? So that's the solution that we're going to get at the end. And remember, the way I interpret this solution is this is the mathematical solution. But the physical solution, I write like this here. I write as IL of 0 minus e to the minus t over tau plus I short circuit of 1 minus e to the minus t over tau. And I call this sort of like the physical solution. Okay. This one's easier to deal with mathematically. This is the physical one. So they have the same form. The only way they can have the same form is if they have the same differential equation. Okay? So let's sort of like I'll show you one step, and then I'm going to move on very, very quickly. So one of the things here that we'll do here is that we do the following thing here. So when I look at my first step here, I want to determine IL of 0 minus. And how do we determine IL of 0 minus? Well, we let the inductor go to a short, and what you're seeing here is that it kills off the 3 ohm resistor, and I'm left with these 2 resistors in the circuit. So what you'll find here is that you get this guy here, which is Vs, and then I'm going to get a 1, a 2, and then I'm going to have the 3 here, and then my inductor here is a short, right? IL of 0 minus is a short, and that kills off that resistor. So I could come in here and I could calculate IL of 0 minus, then has to be, I only have one loop, and that loop tells me that it has to be Vs divided by R1 plus R2. So the next thing that we want to do here is that we want to convert this into a Norton circuit here. So if I come in here, and now I want to convert this into a Norton circuit, what we do then is that I now throw the switch. As I throw the switch, it kills resistor R1. So I'm left with R2 and R3. So when you look at this circuit here, that means at t equal to 0 plus, we saw that the switch is thrown. And so now my circuit looks like this here. I get 2, 3, and then in this case here, I have an inductor here. So this is R2, this is R3, and this is an inductor here. So what we typically do now in this case is we do what? We convert this into a Norton circuit here, and we do the following thing. So now, to convert that, I'm going to remove load. And so then I have a circuit, so then I'm going to determine I short circuit. So if I determine I short circuit here, I'm going to get Vs, then I'm going to get R2, R3, and then what I'm going to do here is that where the load was, I'm going to put a short there. So I'm going to put a short here, and that short is I short circuit. And you can see right away that resistor R3 is gone, and this is R2. So you can see that I short circuit has to be V source over R2. So I got I short circuit. And in a very analogous way, I could come in here and I can determine R Norton here. And if I calculate R Norton here, I'm going to take my circuit, and what do? I remove the load, the source here. And so what I have here is that I have a current that looks like a resistance that's going to look like this. So this is R3, R2, and then when I look at this guy, this will be Rn. And you can see that these two resistors are what? In parallel. Because they're in parallel, that means then Rn is the same as R2 parallel to R3, which is R2, R3, the sum of R2, R3. And then we would then go in and calculate our time constants here. And when we determine our time constant, what we'll see here is that if we want to determine, 1 over tau, tau is L over R Norton. Okay? So if that's the case here, then I'm going to go in here, and you can see that 1 over tau will then be Rn over RL. And then I would then come in and I would stick that into my solution here. And so then our very next step here, in 3 here, is that then we put into solution form. And if I was to put this into solution form here, I'm going to write then that my I short circuit, and of course we calculated this guy here, I would then just put in my values for and then I would solve my circuit problem from here. So I'm going to use the exact same techniques, just like we did before. The question is, why can I use those exact same techniques? Because the differential equation must be the same. So we can derive the first order equation using the Norton form. So if I start off with my circuit here, and the Norton form here, we have I short circuit Rn, and then I have my inductor here. So according to this here, we have a very nice circuit that we can solve here for IL of t here. Now because I have an inductor and that current is changing as a function of time, you can see that there's really only one node, right? We could say that the bottom node is a ground, and then this is the only unknown node. And that node must be the voltage across the inductor, which must be the voltage across this resistor, which must be the voltage across this source here. So, but since there's only one node that I got to consider here, so I'm going to use KCL. So if I use KCL, it must be the current across the resistor plus the current across the inductor. However, the current across the resistor is the voltage of the inductor divided by the current across, divided by the resistance Rn. And if you remember, there's also this inductor equation which looks like this here. So I got to put all of these values into this equation here. And if you look at what you have here, you end up getting something like this here. So I got So I got VL, so I got VL over Rn plus IL. And then this guy's then going to be L over RTH dI dt plus I equals I short circuit. So if I take this equation and I redraw it, so it looks like this, where I divide the value L over R, both sides, you're going to see here that I'm going to get a value of L over RTH over 1 IL, which is equal to I short circuit L over RTH. Now if I define dummy variables, like I did before, here's what I'm going to do. I'm going to define X to be what? IL of T. I'm going to let tau equals L over RTH, and then I'm going to set my K value to be I short circuit over tau. So when I do that, I get the equation that reads dx dt plus X over tau equals K. And this is the exact same form of the first order equation that we got last time. So this tells me here that the solution of T must be the solution at infinity, at its initial value, like this. So I get the exact same form. Everything works exactly the same. So I put quotes over there when I said exactly. What we're really switching here is that we're doing what? We're switching X for the current of the inductor, and the time constant is different, right? Tau is now L over RTH. It's not RC, but everything else works exactly the same. So that being said, I think we should go to the next circuit. Okay? So what I want to do here